All right, we're gonna see if this works. Hopefully we'll get this. Don't have to pause it or anything. This upcoming test, I think it's like 20 questions, 20 multiple choice questions, 6 free response questions. I believe they're evenly weighted. I'm not 100% sure about logistics like that though. I think you can find it all in Learning Suite, so I'm not going to talk too much about that. I'm going to try to get through all this review content as fast as possible. Hopefully will take about an hour. I have really no gauge, never done this type of thing, but hopefully it'll be helpful for you guys. And you can email me with any questions or anything I did wrong. Just let me know. Yeah. All right, so let's just get right into it. I have the concept guide up on a computer. If you guys want to do the same, I'm just going to be kind of walking through the things. All right, chapter 1, drawing and interpreting Lewis dot, condensed and skeletal structures, including formal charges. Let me check it's recording. Yeah, microphone's on. I'm not going to talk about that much. That's something just takes practice. All right, resonance, drawing curved arrow notation, reasonable resonance structures where charge is distributed over multiple atoms or where charge is created to reflect polarity of bonds and availability of lone pairs. Determine most stable resonance structure. All right, this one is really important. It's kind of difficult. Takes a lot of work to learn, but once you get it, it's really helpful for everything else you're going to do in this class. So what I like to do with resonance structures, I like to start with an area of high electron density, like the lone pair right here. Just draw it over to one bond, and then that's going to form a double bond. So I'm going to start drawing it. So as you see, form that double bond, but then there's too many bonds on this carbon right here. So you have to compensate by moving that over to that carbon. And then that's one resonance structure. And then you can keep it moving. Draw it to the next atom, draw the lone pair to there, and then compensate with that, which will do this. So just do it systematically, especially if it's like draw all possible resonance structures. If you don't want to miss any resonance structures, that's going to be the easiest way. One thing, make sure that all of the overall charges of all of your resonance structures are equal. So for this case, they all have a formal charge overall of -1. And how to determine which resonance structure is the major contributor, you're going to look at, let me find, all atoms, making sure they all have octets. Every single one of these resonance structures has a full octet. So that's not applicable. You minimize separation of charges. There's only one charge, so that's not applicable. You maximize covalent bonds. That's done pretty well here. They all have 2 double bonds and that many sigma bonds. We're not going to count it out. And then on this case, the most negative charge is on the most electronegative atom. You can see that this one, the negative charge is on the oxygen, which is the most electronegative atom. So that's going to be the major contributor, or the major resonance. And then to draw the hybrid, you're going to draw the base structure. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I always count carbons to make sure you do that on the exam, just so you don't lose any carbons along the way. And then you draw everywhere there's a double bond and at least one resonance structure. Draw all the partial charges. And then that's your overall, that's your hybrid resonance structure. I was going to do this one, but kind of do the same process with this. If you guys want to practice, you can pause it right here. I'm not actually going to work through it though, so it might not be that helpful. All right, hybridization. What is the shape of sp3 onto 3? sp3, sp2, and sp hybridized atoms be able to draw 3D representation of carbons with different hybridizations, sp3, sp2, etc., and assign hybridization in molecules. Cool. So hybridization, you got the sp3, which means there's 4 electronic groups bonded to your atom. sp2 sp2 means there's 3. sp means there's 2. So if you look at this molecule, this example molecule right here, you can see that this one has 1 electronic group, 2 electronic groups, so that is sp2 or sp. This one has 1, 2, 3, and that's sp2. This one is the same, sp2. So that's the hybridization. And what that means, the sp, so in every molecule, every orbital, so with this one, you need to make 4 bonds. A carbon needs 4 bonds. And if you do the molecular orbital theory for it, it's going to look something like this. There's going to be an s orbital and then 3 p orbitals available for bonding. But if you only have 2 atoms on either side of the carbon and 2 double bonds like this, you want your bonds to be equal. So your sigma bonds to be equivalent in energy. This is energy level. So that's where you're going to form some hybrids. So you're going to take 2 of these orbitals, because there's 2 sigma orbit bonding things right here. And it's going to take 1 of these p orbitals and one of this s orbital to form these 2 hybrid sp orbitals. These 2 orbitals will be 50% s character, 50% p character, and that's what's going to form those sigma bonds right there, right here. And then if you notice, you have 2 leftover p orbitals, and that is going to be what's going to form the double bonds. So you kind of have to know the structure or this in order to be able to draw the 3D representation of those orbitals. This is something that I'm terrible at drawing, so this is really difficult. So you know this carbon, oh, there's a middle carbon too. This carbon has 50% S character, 50% P. If I remember right, S looks like that. P looks like the little dumbbell. So you're going to draw something like that. And then it has 2 of them. And then this one is sp2. And sp2 basically means that 2 of these p orbitals come down to form this hybrid right here. Come down in energy level to form 3 hybridized orbitals right there. Which means that there'd be 33% S character, 66% P character. And honestly, yeah, those orbitals, those hybridized orbitals will look different, but if you don't, if you can't draw the difference, that's okay, because I don't really know the difference. So you could say that's that. So that's one of the sp2 orbitals. Another one is forming this sigma bond with hydrogen. Another one is forming the sigma bond with this hydrogen. Each of the hydrogen only has an s orbital available, so. And then this carbon will be the same. sp2 orbital, sp2 orbital, sp2 orbital. I should have drawn different colors than this and that. So now you have to take into account your leftover p orbitals. This carbon has 2 leftover p orbitals. I'll draw those different colors. So one p orbital is going to look like this on the z plane, and then this one will look kind of like this on the y plane. And then you know that this carbon is going to only have 1 p orbital left over. So it's going to kind of look like that on the z plane. And it's going to form that pi bond, that double bond right there. And then this carbon, because it only can form a double bond with this leftover red p orbital of the central carbon, is going to form is going to have that YP orbital kind of look like that. So I don't know if that makes any sense 3D wise, but that's kind of what I imagine how you want to draw the 3D representation of carbons with different hybridizations. MO theory, be able to draw and recognize appropriate depictions of sigma and pi bonds and lone pairs, determine the polarity of a bond. I think we kind of already did that with this. MO theory is really complex beyond like simple diatomic molecules. But determining the polarity of a bond, the most electronegative one will have the electrons, higher electron density and partial negative charge. All right, moving on to chapter 2, because we are rushing through this. Understand the concept of pKa and how it refers to the acidity of a compound. pKa, if you guys remember from Chem 105, or Chem 106, or 112, I think. I took 106, so I don't know. It's going to be this equilibrium constant, which I don't remember exactly what it is, but it basically is talking about the concentration of the reactants or the deprotonated acid. Let me find it. Ah, here it is. The KEQ. The KEQ, yeah, so it just is this. So deprotonated acid time, and then the proton right there, over the protonated acid. And that's like what KEQ equals. So basically, it's calculating to what extent your acid will be deprotonated in water. So pKa, or not necessarily in water, just where the equilibrium lies between protonated acid and deprotonated acid. The pKa is the negative log of that. So because of that, it's kind of like an inverse relationship where as your pKa goes down, so like a negative 10, a pKa of negative 10 is going to be super acidic, while a pKa of 50 will be very not acidic. And then it's the opposite for the basicity of a molecule. If the pKa is very high, the conjugate base will be very basic. So for instance, we have CH4 up here. Not very acidic at all, actually. And then the base, it's not really basic either, but the conjugate base of that molecule, the carbanion, is incredibly basic, if that makes sense. All right. I'm skipping to 3 because we'll go back to 2. I think 3 is also important to figure out concept 2. So understand and explain the 5 factors that determine acidity, atom, induction, resonance, hybridization, and charge. Rank a series of bases or acids in terms of strength based on these factors. So I'm going to talk about acids. Everything for bases is the opposite. So for instance, as you increase electronegativity, the acidity increases. As you decrease electronegativity, the basic nature will increase. As well as you increase the size, acidity will increase. And that's only for binary acids. That's important. Binary acid means there's only like H plus Cl, so plus one other molecule. So it's like HCl. H2O is also a binary acid, which explains why H2S is going to be more acidic than H2O. HCl is going to be less acidic than HI because the I is bigger. Inductive effect, essentially, if you have these two molecules, where this one has fluorine atoms, which are super electronegative, and this one only has hydrogen atoms bonded to that carbon. The one with fluorine atoms will be way more acidic because it's pulling the electron density away, which makes that hydrogen more prone to leaving or more prone to being attacked. Resonance effect. I didn't leave a lot of space right here, but I knew if I didn't write it out, I would forget a lot of stuff. So resonance effect, we'll do, actually that's, that proton right here is going to have a lower pKa and be more acidic because the conjugate base that extra pair of electrons will be able to resonate and it will be more stabilized. So the conjugate base will be more stable, which means the acid is more acidic. Hybridization effect. I never use this one too much, but it is important. Increased S character is more acidic, kind of like what we were talking about with the hybridization, where this is an SP, means it has 50% S character. This one, on the other hand, this hydrogen and this carbon is sp2, which means it only has 33% S. So this will be more acidic. That will be less acidic. Charge effect. If there's a positive charge on a molecule, it's going to be more acidic. So NH4 has a positive charge, way more acidic than NH3. More acidic. All right, I don't know exactly what type of problem is going to be on the test. We haven't seen the test, but I think there's a good chance that it's going to be something like this, where you're going to have a big molecule and there's going to be a lot of hydrogens, like this. And you're going to have to rank the protons according to their acidity. So the proton that has the highest acidity will be the one that has the lowest pKa, or will follow all of these rules. So we'll use the rules actually to determine this. So looking at this one, this specific proton right here, you can see it doesn't have resonance at all, which is pretty important. It doesn't really have inductive effect because there's no electronegative atoms close by. Hybridization effect, it's sp4 or sp3, which means it's 25% S character, so that's not helpful. So this one, it's not going to be very acidic. All right, let's look at this one now. This one has an electron withdrawing oxygen right here. The conjugate base will have resonance. If you add you can throw the electrons over there and then over there. So that one, is going to be pretty acidic. So I'm just going to put that one at the top for now. And now we can compare this. We can compare C with D. D will have a lot of resonance, but it won't have any electron withdrawing group or inductive effect. It won't have any electronegative atom nearby, so it's not going to have any inductive effect really. So it just has resonance. So that one is going to be less than C, because C has resonance as well as an inductive effect. Then we're going to look at this one, HB. Hydrogen B doesn't have any resonance. The conjugate base won't have any resonance. Yeah, it would just be stuck right there. So it's not, and it doesn't have any inductive effect from any electronegative atoms nearby. So these two are similar in the fact that they don't have any resonance, don't have any inductive effect. They're the same hybridization. They don't have any charge. So then you can go up here and look at the size and the electronegativity. Oxygen is more electronegative, which means this hydrogen will be more acidic than A, because oxygen is more electronegative than nitrogen. I know a lot of you were worried about these being paired against each other, like, let's just say, can't think of any good examples, but like where you got OH2 versus a nitrogen with resonance. I don't think that's going to be like on the test where the fact that the oxygen is more electronegative would make this more acidic. But then this one also has resonance, so that would make this one more acidic. I don't think there's going to be competing factors on the test. Because that gets really tricky to determine. All right. And then with looking at any pair of molecules, number 4 in the concept guide for chapter 2, look at any pair of molecules, be able to recognize the reactive site. Or actually number 2. Sorry, this is number 2 on the concept guide for chapter 2. Predict the outcome of an acid-base reaction and predict the favored side of an acid-base equilibrium. Identify and label acid-base, conjugate acid, conjugate base. So I did this one after I did 3 and 1 because pKa is going to have a big impact on this question, this type of question, and all of these effects on the acidity will also help a lot for this type of question. So looking at this one, what I typically like to do first, I typically like to label it acid, base, conjugate base, and that's pretty easy to figure out. Whatever is going to gain the proton is going to be the base on this side, and then that's going to be the conjugate acid, and then this is going to be the acid, conjugate base. Next thing I like to do is I like to just write out the pKa's of the acid and the conjugate acid. And I think on this test you're going to have a pKa chart. I don't know exactly what pKa chart you're going to have. This is one that I really have liked a lot. So we've got in this problem an alcohol and a water. So water is 14, alcohol is 17. Oh, that's actually carboxylic acid. So we got a carboxylic acid, not an alcohol. Where is the carbon? There it is. So it's 4 and 14. And then with determining equilibrium, the weaker acid between the conjugate acid and the acid will always be favored. So in this case, water, because it has a higher pKa, is a weaker acid, so equilibrium will lie to the left. For this problem, this is a complex molecule. You can see, based on those rules, that this will have a lot of resonance, because the conjugate base will have a lot of resonance over here, because these can move up to there, and these can go up to there, also can go that way. So there's a lot of resonance over there, so that's going to make that hydrogen, what the heck happened? That's going to make this hydrogen be the most acidic. And with that, you know that that's going to be the acid. That's going to be the conjugate base. This is going to be the base. This is going to be the conjugate acid. So this would be kind of difficult to figure out if you didn't have a pKa chart. But you can tell that this is a relatively acidic molecule because all the resonance and also the electron withdrawing with these 4 oxygens. But luckily, I have a pKa chart, so I know that this is a malonate and it has a pKa of 13. And then the conjugate acid has a pKa of 17, which means that this is a stronger acid than this one, so it's going to lie towards the weaker acid. Equilibrium will be to the right. All right, and then this one. I'm not going to use the pKa table for this one. So we can look at, first off, there's a negative charge on this, so you know that's going to be the base immediately. And then this one's going to be the acid, conjugate base, or conjugate acid, and then conjugate base. So you can see that nitrogen on this side has the negative charge, and then oxygen on this side has the negative charge. If we're going to go to our rules over here, let me think about this before I say anything wrong. Oh yeah, increased electronegativity means it's more acidic. So you know that this side, let me think about this. This is in reverse. So the lower electronegativity will be the more basic molecule. So you know that this one, nitrogen, is a lower electronegative, has lower electronegativity than oxygen. So this is going to be more basic than this molecule right here, the oxygen, negatively charged oxygen. And just using that, you can determine that equilibrium will lie that way, because this is a weaker base, this is a stronger base, and you always want to go to the weaker base, weaker acid. You can also look at these, OH versus NH2, using those same rules, the conjugate acid, where the electronegativity is increased, which means the OH is going to be more acidic than the nitrogen. And you want to lie towards the weaker acid. All right. I think that's good for chapter 2. Chapter 3, knowing how to determine the priority functional group and name the molecule accordingly for alkyl halides, alcohols, alkenes, alkynes. That's something you just have to memorize, and also all the characteristics of different intermolecular forces. That's something you just have to memorize and be able to recognize. All right, chapter 4, just moving on really fast. I want to spend an okay amount of time on substitution because that's a relatively difficult topic and introduced right before the test, so it's probably going to be the most difficult thing. All right, so number 1, be able to name compounds. Yeah, that's just something you have to practice. The group that changes the suffix takes priority. Yeah, so practice that one before the test. I don't think there's going to be any naming specific questions, but you will need to know how to name in order to be able to do some of the problems probably. In all the tests I've taken, you've had to know how to name to be able to recognize how to do a problem. Because it gives you a name, and then you have to be able to know how it reacts. All right, 2, draw and identify constitutional isomers, geometric isomers, and stereoisomers. Identify the classification of CON, 1' primary through quaternary. All right, so constitutional isomers, geometric isomers, and stereoisomers. This is something that's always been pretty confusing for me, but from what I understand, you guys have to make sure that I'm correct on this one because I'm not. This was something that I struggled with, is knowing the difference. I understood stereoisomers really well, but understanding which one is a geometric isomer or constitutional isomer, understanding the difference between those kind of got shaky for me. But if I understand correctly, a constitutional isomer, right here, is going to have same exact molecular formula, but different atom connectivity. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Hexane. So that's C6H, XO1. So these are going to be both the same exact thing. I think it's H14. So it's going to have the same molecular formula right there, but as you can see, there's a different connection right here. These are different, so those are constitutional isomers. Stereoisomers have the same connectivity, but different spatial arrangement of their atoms, as you can see right here. Same exact atom, same exact molecular formula, same connectivity, same substituents are bonded to this carbon, but they have a different spatial arrangement. Geometric isomers are a type of isomer that have the same connectivity but differ in their spatial arrangement of atoms around a rigid bond. So a double bond or even a ring structure, those could be geometric isomers. I don't know if those were hit very hard in class, but this is something where this is this is an E isomer. and this is Z, the Z configuration. So this is E, Z. Z is the same side, E is the opposite. And that also could be E, Z. I think it's also cis. Cool. All right, identify the classifications of CON primary through quaternary. That is talking about, if I have a carbon right here, a primary carbon will have no other carbons bonded to it. Wait, let me think about it. A secondary, or actually we'll have one carbon. A secondary carbon, or a secondary carbon, yeah, we'll have 2. Tertiary carbon will have 3. Quaternary carbon will have 4. Let me just double check one thing real quick. Yes, so primary carbon is just the carbon. So those are both primary. And then as you take those bonds and primary, secondary, tertiary, quaternary. And then with nitrogen, it's the same thing. Primary, forgot the hydrogens. Primary, secondary, tertiary. I guess you could have a quaternary. Oxygen is the primary, secondary, and you typically don't see me on that. All right, conformational analysis, butane, rotational isomers, Gauss and eclipsed interactions, determining most stable conformation, draw and interpret Newman projections. I think this is relatively basic for most of you guys. From what I've seen is most of you guys are understanding this pretty well. If I've got butane, we'll say, I don't like red. So with a Newman projection, if you guys remember right, you want to act as if you're looking directly down the carbon, as if this is an eyeball, so that's looking directly that way. And then you got to draw C1 in the front. Where there's CH3, it's facing down. The hydrogens are facing up to the left, up to the right. And then the hydrogen or the carbon in the back will be represented like this. There's CH3, H, H. So the most stable conformation of this will be where the carbons, this carbon 1 and carbon 2, carbon 1 and carbon 4 will be farthest apart. So this is going to be the most stable because they're rotated around that sigma bond to make it so they are farthest apart as possible. A Gauss interaction will be the same thing. Except for those two substituents will be close. So that's like Gauss, they're pushing against each other. What else is it asking for? Eclipsed is where it looks like this. I'm not good at drawing eclipsed. Where they're lined up front and back, and that will always be higher energy than the Gauss because there's a lot of steric hindrance and all right. So we're going to move on to 4, chapter 4. Drawing cyclohexane chair structures, converting flat cyclohexane structures to chair structures with correct stereochemistry. This is a fun one. All right, to start off, so you're going to have this flat cyclohexane. What I like to do first is I like to number all of the carbons. That's something I do all the time in all sorts of problems because I have too many friends, and I've done it too, where in a test, suddenly one of the carbons is gone and you lose a point because you forget a carbon. So the chair structure is going to be a more accurate representation of how the cyclohexane is in 3D space. So to draw it, you draw, that's just something you practice. She talked about how to draw it. So now you can kind of draw the substituents where you know this one is facing up, that is axial, this is here. This is equatorial. And try to practice those angles. They're pretty difficult. I still don't get them right. And I label the carbons 1, 2, 3, 4, 5, 6. So looking at this one, you know that that OH is facing up, which looks like it's the equatorial for this. And if you practice with model kits, it'll just become like intuitive for knowing what is up, what is down. And then this one is facing down. So 1, 2, 3. So we have this, and then we have that on that one. This one looks like it's facing up. This one is facing down, so then the OH is over here. And then to do a ring flip, I'm going to go down because we don't have space. You're going to want to draw the same type of thing, but the opposite angles. And make sure you number your carbons the same. So it's 1, 2, 3, 4, 5, 6. So with the ring flip, what I like to think, everything that was up is still up. Everything that was down was still down. But everything that was equatorial switches to axial. Everything that was axial switches to equatorial. So this was equatorial. With the ring flip, it's going to switch to axial, the axial position. It's still facing up, if you can tell. And then with 3, it was axial, but it's going to flip. Let me think. What's the best way to... I think that's the right angle. It's going to flip to equatorial, but it's still facing down. And one other notable thing, these two alcohol groups right here, they're trans to one another because they're on opposite sides of the cyclohexane. All right. That looks like it is all for chapter 4. Chapter 5, we're getting there. Yeah, just 2 more chapters. Stereochemistry, be comfortable, or concept 1 is stereochemistry. Be comfortable identifying stereocenters and assigning R and S configuration based on ranking the priority of groups. Understand which are optically active. Methyl compounds are not optically active. All right, we're just gonna draw a fake little molecule right here. Actually, all right, that looks good. Okay, so be comfortable identifying stereocenters. To start off, what is a stereocenter? A stereocenter is something with 4 different groups. Cl, carbon, hydrogen, and then NH2. So a stereocenter is a carbon that has 4 different substituents, also called a chiral center. If you look at this carbon right here, you can see that it has Cl, it has this chain of carbons, this chain of carbons, and then implied but not written in, there's a hydrogen back there. So the next thing is like making sure that when you say 4 different substituents, that could be out to infinity. This could be the same going forever and ever, and this could be the same. And then at the very end of this chain, there could be like an OH or something at the very end of one side, and then that would be a difference. So looking at this, these carbons are different immediately. So it's clear that it's a chiral center because this one has the O. But if there wasn't an O there, you'd have to keep going and then look at the second carbon on each side. So this is the second. And then those are the same, or actually this one has 3 H's, and then this one only has 2 H's, so then it's different, chiral center. Assigning priority is the next part of this. Assigning priority, I don't remember all of the rules, but I believe it's basically molecular mass is a higher priority. So looking at this one, you go to the first difference, so Cl right there, that's the first difference. That's going to be priority 1. Different color. And then going to these two, you go to carbon, carbon. This one's double bonded to an oxygen, which I think counts if you're talking about priority order as if it was bonded to 2 oxygens. So then this side is 2, and then this is definitely heavier than hydrogen is, so that's 3. And then you draw an arrow from 1 to 2, 2 to 3. As you can see, it's clockwise, so clockwise is always R. So that stereocenter is designated as the R configuration. This one, we'll do the same thing. There's a hydrogen back there, just not drawn in. Look at this, NH2, highest molecular mass compared to the CH3 or CH2. So this is number 1. CH3 versus CH2, and then bonded to another carbon. This is number 2. And then this is 3. This 1 to 2, 2 to 3, 3 to 1. And then that's S, because it's going counterclockwise. Yep, so that's designating stereocenters. If it's complicated, or if it's more difficult, and it looks like this, where there's an H, CH3, and then Cl, OH. So you gotta assign the orders again. We'll do a different color now. So this is 1, because Cl is the highest molecular mass, 2, and then 3. But as you notice, it looks like it's going clockwise, but the hydrogen isn't facing back. When you're doing the order, doing the rotation, you have to make sure that hydrogen is the back to get the correct stereochemistry, or the stereocenter configuration, RS configuration. So this one is just facing left. So if you can imagine this rotating, the whole molecule rotating this way, flat on the x-plane, horizontal plane, it's flat, and just rotating that way. Then you could almost imagine as if the Cl is now coming out normal, OH is normal, and then this carbon or this methane is right there, methyl group is right there, and the hydrogen would be facing back then. And then you can do the same thing, 1, 2, 3, and see that it is R. So always make sure that the hydrogen's facing back. If it's facing forward, then you just reverse it. So if the hydrogen was right here, then you find the stereochemistry, and then just reverse it. So this one would be 1, 2, 3, that's R. But then because the hydrogen's in the front, then it's gonna become S. Meso compounds. Meso compounds have a plane of symmetry somewhere within them. This is the classic example, I think. So if you look at this molecule, it might not look like it has, actually it does look like it has symmetry. This one's an easy one. But basically you want to make sure that no matter how you rotate everything around the sigma bonds, you just want to rotate it every direction. And if there's any plane of symmetry in any conformation, then it's going to be a meso compound. So you can kind of do a dash. Another thing that I found made this a little easier is actually by doing like a stereochemical configuration by designating R and S. I'll show you real quick the strategy to find meso centers. So this one looks like it might have a plane of symmetry right there because there's the same amount of carbons on either side of this, and the second carbon on either side is bonded to Cl. Oh, I'm tired, sorry guys. But from there, you can look at the Cl. This is the first priority. This is going to be the second priority going this way. 1, 2, 3. So you can see that this is R. And then if you go to this one, this is the first priority. This one is the second priority. This one's the third priority. It looks like it's R as well, but the hydrogen, there's an implied hydrogen right there that's facing forward. So it goes from R to S. So the little hack is if you see a line of symmetry that looks like it could be symmetrical, but you're not 100% sure, just draw that line and then take the stereocenter on either side. And if they're opposite stereochemical configuration, then it is a meso compound. I don't know exactly why that works, but it does. And that's a really analytical way to think about it rather than just trying to like imagine lines being drawn through molecules. Calculate the total number of possible stereoisomers possible for a molecule by identifying n number of stereocenters, and then total equals 2 to the n possible isomers. Cool. So this molecule has 2 stereocenters, one R, one S. So 2 to the n is going to be, so it's going to be 4 stereoisomers are possible. With that, there's always going to be the original molecule, the enantiomer, and then the rest are diastereomers. All right, now talking about enantiomers and diastereomers. The enantiomer, we're just going to take that same molecule. Actually, different because that's a meso compound. So this is a new molecule. We're going to talk about what an enantiomer is and what a diastereomer is. Sorry, I don't know how much time it's been, but it feels like it's getting long. I'll try to finish up. So, an enantiomer is a non-superimposable mirror image of the original molecule. So this one you can, I've never good at actually imagining like what it's gonna look like. So I've always done this analytically by designating stereocenters. 1, 2, oh, that's wrong. This is 2, this is 3. So you know that this is gonna be S, and then this one is going to be 1, 2, 3. It's also going to be S. So both of these stereocenters are designated S. The enantiomer is going to be that same exact molecule, but all stereocenters are flipped exactly. So for instance, you can do there we go. Yeah. So as you look right here, all of the original stereocenters are flipped exactly. And you can do this analytically by designating the stereocenters RRS, where this is 1, 2, 3. So it's going to be going counterclockwise, but the H is going forward, so it should be going clockwise, which means this is R, 1, 2, 3. So it's going counterclockwise, same thing, H is in the front, so it switches to R. So all stereocenters will flip from, if they're S, they'll go to R, if they're R to the S. And that means they are enantiomers. If you want a diastereomer, it's going to be that not all of the stereocenters flip. At least one flips, but not all of them. So this one, 1, 2, 3, it's an R. This one is 1, 2, 3. Oh, that's not right. 1, 2, 3, counterclockwise, S, 1, 2, 3, counterclockwise, but H is in the front, so it switches to R. So this one, only the right stereocenter flips, so it's a diastereomer. All right, I think that's good. There's the math stuff and enantiomeric excess. I think that is relatively simple. I'm not going to go over that type of problem for time's sake. But yeah, I think that's good for chapter 5. Last chapter.